David Smith here with one more flipped classroom math lesson. 3 tips before we start. First, remember that you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to jot down some notes or write down some questions for our next class. Lastly, you can turn on the captions so you can read my words go by on the screen. Today's lesson covers a correlation coefficient that's different from R. So we did the Pierson correlation coefficient a while back, and that would tell us how strongly the data were correlated for linear relationships. Spearman's ranking system allows us to measure correlation for non-linear relationships. Big distinction, because you could have a really strong correlation with something that's non-linear, and Pierson's would not be good. So, R is Pierson, R sub S is Spearman's. So here's how we define it: the product moment coefficient of the ranks of a data set. So this works with nonlinear data, whereas we use R with linear data. So you want to remember how to do R, because you're going to calculate both of these together in a lot of the problems that we're going to do. And just a word of warning, the ranking process is a little tricky. So pay good attention to that, make good notes, and make sure you practice it correctly. Okay, let's do a problem. So here's our data. This is potentially realistic data. We've got training time in hours, presumably for some people or some athletes. And then we have a 2K run time in minutes. And these are each data points. And our assumption is that, yeah, if you spend more time training, your run time is going to be a little bit faster. So cool, I like that. Now, what you want to do is create ranks for your data. Okay, let's do some ranking. Pay attention, this can be a little bit tricky. What we're going to do is we're going to rank each of the X and Y parts of the data set, starting from highest to lowest. Okay, so looking at the X values, you have to keep track of where you are counting down. So my highest one is 1. That's the highest rank, that's the first rank. The second highest would be my 34. That's my second rank. My third highest is 29, so that would catch my 3. Now my fourth highest, there's a tie. I have 2 at 23. So what we do is we split the difference and put the average rank. That way it doesn't weight one data point more heavily than the other. So this would normally be 4 and 5. These would be 4 and 5, so we're going to split the difference and call it 4.5 for both of those. Okay, that's a little bit of a tricky thing. Now we've used up 4 and 5 with these, so our lowest rank is 6. Okay, so a little tricky, but not complicated like algebra complicated. You just have to think your way through it. Now what I want you to do is pause the video and rank the Y values. Okay. Counting down from the highest value, the first ranked value, we have a 14, that's the highest number in the Y value, so that's rank 1. Then we go down to 12, that's rank 2. And then we go down to 11. So 11 is going to be 3 and 4. So we put 3.5 in for the 11, and we've used up 3 and 4 there. So the next lower one is 5, and finally our lowest value is 6. That's how you rank your data points. Okay, so now that we've established our ranks, we make a new table with the rankings. Okay, it's kind of weird. What we're going to do is we're going to exchange the ranks for the data. So this is the 23-12 point right here, but 23 is 4.5 in the ranking and 12 is 2. So I replaced the data point with the ranks and I just went all the way on down. Now, keep track of what you're doing. Again, not fancy algebra, but it's easy to get a little discombobulated and put the wrong thing in the wrong place. So you got to be really careful about that. And again, to review these 2 main points: replace the data with the ranks. Second, keep the order from the original data. So I'm just going through the data the same order that I went there. Now this is kind of weird, because now we're going to use the ranks to calculate R sub S. So we actually don't use the data to calculate this particular correlation coefficient. All right, here comes the moment. We are going to calculate the Spearman's rank coefficient. So it's actually no different from calculating the Pearson's coefficient. In other words, R, Pierson, gets calculated the same way as Spearman, R sub S, with one exception. Instead of putting the data in L1 or L2, you put the ranks in L1 or L2. So now's the moment to brush off your skills with your fancy calculator and go ahead and find R for these points. They're not data points, they're ranking points. But put your ranks in L1 and L2 or in a spreadsheet if you use the Inspire, and go ahead and initiate your regression, your linear regression calculation, and find your R sub S. And come back. Okay, here's what I get. Minus 0.956. Now pause the video again. Think a little bit. What does that number tell you? Think about what R told you. We're going to use the same descriptors for R sub S. So pause for a minute. Think about what that told you and then come back. Okay, it's strong negative correlation. The negative, obviously, right there. And then strong because it's above negative 0.75. We don't say linear because we're not doing a linear correlation. So don't throw that in there when you're using Spearman's. Okay, let's do another example. This one's going to make a different point, but I'm going to wait until we get there. So check this out. Our situation here is, the basic question is, if you put more fertilizer on your ground or mixed in with your soil on a farm, are you going to get more growth? More fertilizer equals more growth, question mark. Now, of course, intuitively, we would say, sure, yeah, plants need it, give more, plants grow more. Makes sense. But since we're hired to do this and make recommendations and people are paying us lots of money to spend even more money on fertilizer, we want to be sure we know what we're talking about. Enter statistics. So here we go. We went out to 10 different farms and we measured things, or we asked the farmers things. Whatever we did, we got amount of fertilizer and yield for all these different farms. And that's a good start for using data to be more sure of what we're going to make recommendations to for future farms. So I want you to do what I call data snooping. Just look at that data and see if it supports your hypothesis or not. Okay, if you said yes, you're right. Check this out. 10 kilograms per hectare got us 20 kilograms of crop. We don't know what the crop is, but 20 kilograms of crop. In contrast, if we put 45 on there, we got almost 40 kilograms of crop. Similarly, if we put 5 on there, we get only 12. So, and if you compared the rest of the numbers, you'd see that trend. So based on data snooping alone, we're feeling pretty good that this is correct. But since we're professionals and our reputation is on the line, we want to crunch some numbers. So the first number to crunch, R. Find the Pierson correlation coefficient. So put these in one column in a spreadsheet or in L1 on your 84. Put these in L2 on your 84 or another column and go ahead and run your regression and come back with your R value. Okay, when I do this on my calculator, I get a 0.881. So this is, as you know, a strong positive correlation. Okay, so now we're feeling pretty good. That's a good R value. But let's up the stakes. The country of China is looking at your recommendation. And if you do a good job and get good results, they're going to give you $1 billion contract for consulting in their agricultural industry. Well, high stakes. This would make you wealthy beyond your dreams. So would you stop here? I wouldn't. Yeah, strong positive. I'd like to really know. I can see that from snooping on the numbers, it doesn't look like it's linear. So since it doesn't look linear, I want to use a non-linear analysis on this and see what the correlation looks like that. And luckily, we have the Spearman's rank coefficient. So our first step is rank the data. So go ahead and carefully rank your data, giving 1 to the highest and counting down from there to the lowest value for both the X and the Y. Come back and we'll see how you did. Okay, let's see how you did. Now, if you did it the way I did here, you probably noticed something about this data, which would probably give you a feeling that it is contrived, which it is. So the rankings match up perfectly. The highest amount of fertilizer ranks with the highest yield. and so on all the way down the line. So this one is set up to do just that, okay? So now in L3 and L4 on the 84, or make 2 new columns on your spreadsheet in the Inspire, go ahead and put in your ranks. So your L3 or your X coordinate would be these numbers, and your L4 or your Y coordinate in your spreadsheet would be these numbers. Go ahead and put those in and calculate your Spearman's rank coefficient. Come back. All right, so I got 1. Now again, contrived example, so that's why we're getting 1. In real life, you'll almost never get 1. And what that means is that there's a perfect correlation in the order of increasing. It increases the same way every time. So the highest amount of fertilizer added also corresponds to the highest yield. So that's why we got a 1.0. Now, if this is my data and I was going to show off for a big customer, like perhaps the country of China is going to give me $1 billion contract, I'm going to do this second correlation coefficient just to be sure that my work is good. And when I get that, I'm pretty sure. Okay, to bring this point home, I wanted to graph our data. This makes it really clear what's going on. So then I put our R, 0.881, and I put our R sub S, 1.00. Okay, so check this out. It's a curve. It's not a straight line. Okay, so right there, that gives you a feeling for why R might not be the best, because the data doesn't follow a straight line. It's just not a straight line relationship. Let's go to reality for a minute. You can imagine this would be the case. There's a point of what we call diminishing returns. A plant only needs so much fertilizer. After that, it's happy. So if you put 10 more kilograms in there, it's like, fine, but I don't need that. So I'm growing already at my max rate. So you're not going to get an increase of yield past a certain point. And it looks like that might be maybe 30 kilograms. So why spend on 20 more kilograms per hectare? It's a waste of money, basically. This is like the sweet spot right in here. So that's not a linear relationship. After a point, you don't get the same increases. So that's why this is 0.881. Now, the R sub S is 1.0 because every time you increase the fertilizer, you get an increase in yield. There's not a time where that doesn't happen. All of our data points show more fertilizer means more yield. So the ranks are the same. That's what you noticed in that last table. We had our ranks going across the same. So to summarize, R is for linear relationships. R sub S is for relationships that are not linear, but that make curves on the graph. Last prompt. Can you think of a real life example that follows a nonlinear relationship where R sub S might be more valuable for trying to understand the strength of that relationship? Pause the video and write that down before coming to class, because I'm going to ask you about it when we meet next. Now that you've watched the video, jot down some notes, some questions, or a quick summary of the lesson. You can also re-watch the portions of the video that challenged you the first time. If you enjoyed the video, please click like. If you'd like to help me grow my YouTube channel, please click subscribe.